right, guys, this is the part 2 of the work-energy theorem. So I'm going to do the problems, and really the problems are all conceptual, every single one of them. So you just have to know how to actually translate this change in energy equals the external work done on the system, right? So you just have to figure out how to do the bar charts, right? Depending on what you choose as your system. All right, I think this will work better if I turn on the projector. All right, so just wait. So again, it's all going to be about writing this equation in a chart form, and depending on what our system is, the external work will be different each time. Here it is. Okay, so the first question, these two objects on level ground have different masses but the same kinetic energy. If you stop them with the same force, which one will stop in the shorter distance? Well, I think since if it's level ground, the only thing we have to deal with is basically kinetic energy. So I can say, or I showed you also, that the net work done here is the change in kinetic energy, right? And the only work the force that's acting on this is basically this force of friction trying to stop you. Now, so the change in kinetic energy is going to be the same for both of them. Now the work done here is going to be negative F times D, because you're going to be moving one way and the force is the other way, so you're going to have a cosine of 180. Now, since the force is the same, the distance will have to be the same. Okay? Now, I'm going to just add another question to this. So, if I double, and we did this in kinematics, if I'm going at a speed v, right, and I double my speed, and let's say when I'm going at a speed v, I was able to stop at a distance d, what would be my stopping distance, right, in terms of d, if I double the velocity? Well, here, assuming the same force, I'm going to do the same thing. The work done by this force of friction equals change in kinetic energy. In here, negative F times something equals, now the change in kinetic energy here is going to be 4 times as much, because the velocity, the kinetic energy is proportional to the velocity squared. So this is going to be 4 times what I had up here. Okay? And the change is going to be negative, obviously. So this question mark here is just going to be 4 times d. We talked about this in kinematics, and I'm just talking about it now with energy. Because really all the energy equations came from F net equals ma and from kinematics. All right, so in this RT4, it says, is the horizontal force, I read the problem already, so is the horizontal force acting on the javelin in case A greater than, less than, or equal to case B? Well, there is no force really acting in the horizontal direction, so basically there is no force. Okay? So it's basically 3, which is basically 0 force. 0 newtons. Okay. The next one, number 5. The student states the initial kinetic energy is 9 joules. Okay. So it's 1/2 times 2 times 3 squared. Final is 49. Same thing, 1/2 mv squared. Thus, the change in kinetic energy of the object during the 5 seconds is 40. Okay. And the work done on this object, or the net work during this period, was also 40 joules. Well, here we don't have any change in height. What, if anything, is wrong with this statement? There is nothing wrong with this statement. So, okay, so the net work is basically changing kinetic energy. Okay, so there's nothing wrong with this. Okay, next one. And in the next one, in the answer key in the packet, I talked about force of friction, but it's not the force of friction that's stopping you. It's the force from the barrels trying to not let you go forward. Rank the strength of the forces, magnitude of the forces that will be needed to stop the car in the same distance. Now, it's going to be negative Fd, the work done by the force. So you move in this way to the right, the force is acting to the left. So it's going to be negative Fd, okay, equals change in kinetic energy, right? Again, I'm just using my work-energy theorem, right? At the end, I'm going to have 0 kinetic energy minus the initial kinetic energy. The distance is the same, so I don't have to do anything there. So basically, it's going to, in order to compare the force, you just have to compare the initial kinetic energy. So that's really what we have to do, since the distance is the same. So all I have to do here is find the kinetic energies for all of those cases and compare them. So it's going to be 18,000, 51,200, 38,400, 12,800 for A, B, C, D in that order. So the answer would be B, C, A, and D. Okay. Now, rank the work done on the box by the external agent for the 5 seconds. Okay. Now, this is moving on a horizontal line, surface, straight line. So you just got to be careful here. This is a VT graph. The area under the curve in a VT graph does not give you the work. Don't confuse that with the an FT graph. That's the one. FD graph. That's the one that gives you work. FT graphs gives you something else. We'll learn later. Now, if you want to find the work done here, okay, and assuming that's the only force acting on the object, so we're looking at the net force. That's the change in kinetic energy, right? And assuming that's the only force. Now, all you have to do here is you find the change in kinetic energy for each one of these parts here, okay? And if you don't want to deal with that, you can actually see that in A and D, in D you're not moving, so the change in kinetic energy is 0. In A, you're going at a constant velocity. Kinetic energy, the change in kinetic energy is 0. For B, the change in kinetic energy is positive because you're going from a low speed to a high speed. So this is positive. And in part C, you're going from 6 to 0. So you're going to end up a negative change in kinetic energy. So the order should be B, A and D are tied, and C is negative. Okay? Now I'm going to go to RT8. Okay. Force pushing box changing kinetic energy. A box is pushed 10 meters across the floor in each case. All boxes have initial velocity of 10 meters per second to the right. So they're giving you the mass and they're giving you the net horizontal force. Okay, so we're talking about the net work here. Rank the change in kinetic energy. Well, work net is equal to change in kinetic energy. So instead of ranking the change in kinetic energy, which I cannot do directly, I don't have the velocities, so I'm just going to look at the work done by the net force. Now that's going to be the F net times the displacement. Okay? And I think the displacement is the same. Yeah, a box is pushed 10 meters, so the displacement is the same. So this D is the same. So basically, in order to compare the kinetic energies, all we have to do is compare the forces. So it looks like D comes first, A and B are tied, and D are next, and C is last. So sometimes if you want to do the change in kinetic energy, you can't do it directly. You have to rely on the work. Okay. Now for RT9, a student, so the student wants to compare the net work done on the two boats between the 2 points. I think that more net work was done on the boat in graph A because it's moved further during the interval between these 2 points. Well, actually, the net work is changing kinetic energy. Now, this is a position time graph, okay? And this is a straight line here. Okay, it's not a curve. So basically, the velocity remains constant in both cases. So in both cases, there is no change in kinetic energy, which means there is no work. Okay? So the student is wrong for that reason. Now we're going to go to RT10, which is a couple pages down. Right here. Okay. Okay. So now we have to start doing some of these bar charts. Now, this velocity went from 2 to 4 meters per second. Now, the velocity doubled, okay? And which means the kinetic energy will be 4 times as much. The fact that we put 2 bars here has nothing to do with the fact that this is going at 2 meters per second. It's just a coincidence, right? I could have just put 1 bar here to represent the kinetic energy initially, right? So the kinetic energy will be 4 times as much as here. So the kinetic energy here will be 4 times what it is here, because of that square on top of the v squared in the 1/2 mv squared equation. So kinetic energy will be 8 bars here, 4 times as much. 2, 4, 6, 8. So I'm going to be here. Okay. Now, according to the Work-Energy Theorem, energy before plus any work done in between equals the energy later. Well, if this is 8 and this is 2, I should have 6 bars of work done on the system. The next question is exactly the same thing. It's probably counterintuitive, but the reason it's the same thing is because energy is a scalar quantity, so we really don't care about which way we're going. The forces and the displacements might be different, but when it comes to the energy in both cases, A and B, are the same initially and finally. Okay. Objects changing velocity, work and kinetic energy bar charts. Okay. A 2 kilogram object is all. So this is a 2 kilogram. Okay. It changes its velocity from 4 meters per second east to 6 meters per second west. We don't care about the east and the west, right? And the reason for that, because again, kinetic energy is all scalar. Okay, so the kinetic energy initially is going to be 1/2 mv squared, right? So that's going to be 16 joules. So we'll figure out how to represent that later. Later, later it's going to be 1/2 times 2 times 6 squared, which is 36. So we have to figure out how to do this. How about if we make, how about if we make every bar of 4? Yeah, 1, 2, 3, 4. And I'm going to need 9 on the other side, which I think I have. Yeah, 1, 2, 3, 4. And on the other side, I need 9. 2, 4, 6, 8. I think I just about made it. Okay, so it'll go all the way to the top here. You just have to, I think you could, if you do, I don't think you can do any other way. If you want to have whole number of bars, unless if you want to do with the halves, right? So if you do a 2 here, you end up with 4.5 bars in there, which is, I think, okay, I think. All right. Now, if this is 4 and this is 9, it's got to be 5 bars of work. 1, 2, 3, 4, 5. So we respect the Work-Energy Theorem formula that we came up with last time. Okay. Oh, there are two questions with that. Okay. I think I passed this. Did I do? Yeah. Okay. So we're on RT11. Sorry, I just had it in the wrong place. Okay. Now we're looking at RT12. Okay. So now just pay attention to things like we're pushing at a constant speed. Okay. Okay. So let's just say, I really don't know. I'm just going to make 2 bars here. Since we're pushing at a constant speed, I should have 2 bars for the kinetic energy on the other side. Now, put the 0 point for the gravitational potential energy at point A. Okay, so which means initially there was no gravitational potential energy, right? There's no spring involved here. And that doesn't tell us what to pick as this. Well, yeah, we have to pick the Earth and the block as the system. So this idea of gravitational potential energy is there, right? So now we're going to have gravitational potential energy when we get up to the top, okay? So I'm just going to pick 1, 2, 3, 4. It's just, I don't know how many, right? Now, these don't look equal, right? And I think what we're missing here is that the hand is doing some work to move up the ramp, and that's positive work. So whatever number of bars you have on this side plus whatever you have on this side has to equal here. So I think I need to put 4 bars here so that the equation holds true. And I think in the packet I did it differently, but the bottom line is that whatever number I have here combined has to equal to whatever number I have on the other side combined. Okay, now we're on RT13. Now they're giving you the velocity, and so it's going west. So this is what's happening initially, and this is what's happening at the final state, right? Complete the work and kinetic energy bar chart. So I'm going to come here and I'm going to just pick 2 bars, not because of the 2 meters per second, but I'm just going to pick 2 bars. Okay. Now, if the velocity doubles, the kinetic energy will quadruple. So I should have 8 here. 2, 4, 6, 8. That should put me there. Okay. Now, how much work is done? Well, to go from 2 to 8, I need 6. So here's my 6. Okay. This one is the same concept, except this time you're going from 4 to 2. Okay. So the velocity is cut in half, so the kinetic energy is cut in 4. So I'm going to do 8 here, and I'll do 2 at the end here. Okay. So now I need to subtract something from the 8 to get 2. So I have to subtract 6. So there's negative work being done. And that kind of should make some sense. If you're slowing down, it means you're decelerating. It means like there's got to be a force opposing the motion. Okay. Okay. Just make sure. Okay. 100 Newton box is initially at rest at point A on a smooth frictionless surface. Horizontal surface student applies. So there's a force of 80 newtons being applied. Complete the energy bar chart. So this is after it moves 5 meters. Okay. So the work done by this external. So I think there is no energy in the beginning, right? There's no kinetic, there's no gravitational potential, there is no elastic. So I think we're just going to have 80 times 5, which is 400. So I guess I can make that as 100 per box, right? Okay. And the only thing that's going to change is that I'm going to have kinetic energy at the end. So I should have same number of bars. Okay? And you don't have to do 4. You can do whatever you want to do. Okay. All right. Okay. 100 Newton box is initially 0.4 meters above the surface of a table. So this is the table. This distance here is 0.4 meters. And it's moving upward with kinetic energy of 80 joules. Okay, so it has some kinetic energy here. In the initial phase, it has 80 joules of kinetic energy. A man is applying a constant upward force of 80 newtons with his hand to the box. Complete the energy bar chart. Now the earth and the box are the system, and the box has moved 1 meter. Now it doesn't put the 0. Okay, so this is the reference for gravitational potential energy. Now when we are up here, this is 1.4 meters. Okay, so we have 80 joules of kinetic energy, that's given, right? Now we apply a force of 80 newtons over a distance of, let me see, 80 newtons over a distance of 1 meter, so that's another 80. Yeah, so that's another 80 here. Okay, we do have some gravitational potential energy, and the gravitational potential energy is just going to be mgh. Now the mg is 100, and the height is 0.4 because we're choosing the table as the reference. So that's 40. So that should be half of 80. So gravitational potential energy is here. Now we have no spring, and when we are at the very top, I think we can figure out the mgh. The mg is 100, and the height with respect to the table is 1.4. So that's going to be 140. So each box is worth at 20, it looks like. So I need 7 boxes for the gravitational potential energy. 2, 4, 6, 7. So I'm up here. Okay. Now let's do the math and see how much we need to give to the kinetic energy. I have 6 here. I have 4 here. So I have 10 altogether. Here I only have 7. So I think the kinetic energy needs to get 3. All right. Okay, so this box here is 1 meter above the ground while moving with a speed of 10 meters per second. So it has some kinetic energy here. And that kinetic energy is going to be 1/2 of 10, so it's going to be 500 joules. Yeah, this should be 500. Okay, I made a note of that. Yeah, that's half. The mass is 10, right? Let's just make sure we're doing this right. Half of 10 times 10 squared. Yeah, so that's 500 for sure. Okay, and a student starts applying a vertical force of 100 newtons, 120 newtons upward with her hand at this point. Complete the energy bar chart. Okay, so do we have gravitational potential energy at this level? Yeah, well, with respect to that point down there, we do. So how much gravitational potential energy we have? We have 100. So it's mg, which is 100 times the height, which is 1. So we have 100. Okay. There's no spring involved. Now the girl is pushing on the object up. Now, how far up does she push? Now she pushes a distance of 1 meter with a force of 120. So this is not going to be nice, but we should do 120 here. So just be aware that this is not on the line, but it's just a little bit above it, 1/5 of the next line. Okay, so now are we going to have gravitational potential energy? Now the box is 2 meters above the starting point. So now the kinetic gravitational potential energy doubled. So that's going to be 2 bars here. Okay, so now the difference has to give us the kinetic energy on the other side. So what do I have here? I have 6 bars. Here I have 2 bars, so I need, actually 6, 7 and change. So I guess we can say that's 720. Yeah. Here I have 200, so I have to figure out. So I'm going to have to give 520 to the kinetic energy. 1, 2, 3, 4, 5, and a little bit. Okay, and that's what it should look like. Okay, number 17. It's kind of like the same one, except I think now we're going to change the 0. So the 0 will be up here, okay, at the final place, basically. Yeah. All right, so this distance here is initially above the ground. Students start applying. Okay, so this distance here is just 1 meter. Yeah. Student starts applying. Okay, so this is this is 500. Now, do we have gravitational potential energy here? We do, but it's negative because they are below the point. So that's 100, but negative. So here is a negative 100. Now, the work done by the person, it's 120, just like before. Okay. And the gravitational potential energy at the very top is 0. So there's nothing here. So let's just do the math here. So let's figure out the kinetic energy. So I have 500. So basically it's 400, right? And 120, it should be 520. So I should have 520 here. I hope that made sense, because we changed the reference point for gravitational potential energy to be at the top, so we have no gravitational potential energy at the top, and anything below that will be negative gravitational potential energy. Okay. A 40 Newton box is initially at rest on a smooth, frictionless horizontal surface. An end-stretch spring with spring constant of that much connects the box to the wall. 16 years. Okay. Complete the energy bar chart for the spring block earth system as the block moves a distance of 2 meters. So we're going to compress the block by 2 meters, right? Yeah, so there is some work being done, and the work is basically 60 times 2, which is 120. Okay, so I don't know how I did it here. I did, in the answer key, I did every 20 joules is a box. You don't have to do that, but let's just stick to what I have. 1, 2, 3, 4, 5, 6. So that's the work done by the force. We apply 60 newtons, right? And for a distance of 2 meters. Okay. It's applied horizontally to the right. That's fine. Okay, so we're pulling it instead of, I thought it was compressing it, but we're stretching it. Okay. Now, initially, we're starting from rest. So there's no kinetic energy. There's no gravitational potential energy. This is on a flat surface. Now, initially, there is no energy stored in the spring. right? Because he was not stretched. Now let's figure out if there is any energy stored in the spring after we apply the 60 Newton force to the right. Well, the energy stored in the spring is basically 1/2 k x squared, so 2 squared. So this is going to be 5 times 4. Okay, so that's 20. Okay, so that's 20. So that's going to give us 1 box of energy in the spring. Okay, and the rest will have to be kinetic. Okay. So now we're compressing the spring, right? And we're picking the earth, the person, and the spring as the system. So we're going to talk about all kinds of mechanical energies. Okay. Okay. So the gravitational potential energy is not going to change, so it's going to remain at 0. Initially, this starts from rest. Okay. Now, everything that they have is stored in the spring. So I'm just going to randomly pick 2 bars for energy stored in the spring. Okay? There's no external work done. I guess it's frictionless surface. Yeah, ignore friction. And when they leave, the only thing they're going to have is basically kinetic energy. How much kinetic energy? Well, the same amount of energy that was stored in the spring. Okay? And we do this one here, and I think this is the last one. Yeah, it's the last one. All right. It's the same as before. So there's no kinetic energy. There's definitely energy stored in the spring. So I'll just pick 4. Okay. There is no friction. So basically there is no external work, and the system includes the Earth. So Earth does not do any external work. And then we have to deal with the kinetic energy. Are they going to have kinetic energy at the highest point? No, they don't. And all their energy now is in the form of gravitational energy. Now, I'm just going to change this a little bit. Let's see if we decide not to pick the Earth as part of the system, right? Okay. So if we don't pick the Earth as part of the system, between the moment he leaves the spring and getting to the top, Earth is doing some work, some negative work, right? And how much negative work is it doing? It's doing this much, 4 bars, because at the end, based on the system we picked, there is no energy left. So basically, whether you do it on this side or the other side, it doesn't matter. Oh, there's more. Okay, so there's one more, sorry. Okay. Okay. A rock is dropped by a student from the top, falls straight to the ground. So this person picks this point as 0 for gravitational potential energy. It dropped, so there is no kinetic energy in the beginning. There is no gravitational potential energy because they picked that point as their reference. There is no spring involved, right? And they don't tell us what to pick as the system. So I'm going to assume Earth is part of the system. You can try that, right? So when the ball is down here or the rock is down here, it's going to have kinetic energy, and it's going to have negative kinetic energy. So that's good. Okay, so now let's see what they're asking us to do here. Okay, draw a new energy bar chart for this event, but use the ground as the 0 point for gravitational potential energy. Okay, so that's not too bad. So here, you're going to have one, I don't know how many bars they pick, but I can pick whatever I want. 1, 2, 3, 4, 5, let's say. Okay. And there is no external work, there's nothing else. So the only thing is like all that gravitational potential energy turns into kinetic energy at the end. Okay. Now let's just add to this, and let's say we're going to pick the lowest point as 0, and at the same time, right? Actually, let's try this. Let's set it up so that the Earth is not part of the system. So this concept of gravitational potential energy is not there, and Earth will be doing some positive work. Yeah, some positive work, because gravity is force of gravity is down, and you're moving down, so you're doing some positive work. Okay, let me.
All right, I'm out. Peace.